Okay, so what is up, guys? I wanted to bring back a little discussion about Lewis dot structures. One of the things I want to say is that previously, when we've studied our Lewis dot structures, we've assumed that all the atoms involved in a particular molecule, when we have a molecule, we assume that all those atoms are going to end up having a full or filled valence shell. So typically, that would be following the octet rule, in which those atoms end up having 8 valence electrons in order to have that full shell. What we're going to talk about today, and I'm going to show you examples of a few Lewis dot structure octet exceptions. So the first are going to be aluminum and boron. These elements these elements can have less than 8 valence electrons, and we'll find to have 6 valence electrons in our examples today. And then our others are phosphorus, sulfur, bromine, and iodine. And these elements can have more than 8 valence electrons when we're forming different molecules. First, we're going to start with aluminum and boron, and we're going to see how they end up forming these molecules in which they have less than the 8 valence electrons. I'm going to start with aluminum. It's going to be bonded to 3 bromines. So our aluminum is going to be the central atom. I'll go ahead and draw it. Along with its valence electrons. Aluminum has 3 valence electrons. I know this because it is in group 3A of the periodic table, and so it's going to have 3 valence electrons. With my bromines, I'm just going to space them out around my aluminum. I have 3 bromines, and I have 3 valence electrons for aluminum, so I'm just going to go ahead and put a bromine by each of these valence electrons. And then I'm going to add bromine's valence electrons as well. So each bromine has 7 valence electrons because it is in this group 7A. So what we're going to see here is this is pretty simple. Bromine is just missing 1 electron in order to have its octet. And so what I can do is it's bromine and aluminum, they're going to share these 2 electrons for each. So aluminum is going to share this electron with bromine, bromine is going to share this electron with aluminum for all of our interactions here. So since they're sharing these electrons, we can go ahead and represent these as covalent bonds or single covalent bonds. And so when we're looking at each of the atoms involved here, my bromine atoms, we've got 2, 4, 6, and then since they're sharing these 2 electrons between aluminum and bromine, I can count both of them for bromine as well. So bromine will have 2, 4, 6, 8 electrons. Each of my bromines has 8 electrons. That octet rule is satisfied, so my bromine has a full valence shell. My aluminum, looking at this central atom, however, my aluminum has 2, 4, 6. So it's going to be one of those exceptions. So from here, what I can do to determine the molecular geometry of this aluminum bromide molecule, I look at my central atom. I'm going to look at aluminum. So the number of electron groups that I have here, I've got 1, 2, 3. And I know that all of these three are bonding groups. We have no lone pairs. So from here, I can look at my molecular geometries chart that I gave you guys on Monday. And with 3 total electron groups, my overall electron geometry is going to be trigonal planar. And then because all 3 of these groups are bonding groups, I'm going to end up having an overall molecular geometry that is trigonal planar. So the shape of my molecule is going to be trigonal planar. So when I ask for the shape of the molecule, I'm talking about the molecular geometry and not the overall electron geometry. So moving on here, we're going to look at boron trifluoride. And this is going to be a situation that is very similar to aluminum bromide. So again, I'm going to use my boron as my central atom. Boron also has 3 valence electrons, and then I have 3 fluorines. So I'll go ahead and draw those around my boron. Very, very similar because fluorine also has 7 valence electrons, same thing as bromine. And so it's going to form a molecule that's very similar. And this molecule also has a molecular geometry that is trigonal planar. So again, I determine molecular geometry by looking at my central atom and looking at the total number of electron groups. There are 3. Since all 3 are bonding groups, I can use my molecular geometries chart, and I see that the overall electron geometry is trigonal planar and the overall molecular geometry is also trigonal planar. So my molecular shape is going to be trigonal planar. Now, this gets a little bit trickier when our central atom is going to have more than 8 valence electrons. So I'll show you how we deal with that. I'm going to first use one of the exceptions that I did not list, and it's going to be xenon tetrafluoride, so ZeF4. So again, this one is an exception. It is an exception for a few reasons. Xenon is a noble gas, so it's generally unreactive, but it is known to undergo a few different chemical reactions. So what I'm going to do first is I'm going to write xenon as my central atom, and then I will add its valence electrons. So we know it's a noble gas. It's in group 8A, so it's going to have a full shell of full 8 valence electrons. So I've got my xenon. Now what I'm going to do is I have 4 fluorines. I'm going to space those out evenly around xenon. And then I'm going to add fluorine's valence electrons. So again, fluorine is in group 7A, so it's going to have 7 valence electrons. So what I'm going to do here, now that I have fluorine's valence electrons, I'm going to look to see how I can pair these up so that each of my fluorines end up with 8 valence electrons. So what I see is like each of my fluorines is missing 1 valence electron in order to have that full octet or that full valence shell of 8. So I know that my xenon is going to donate, or not donate, but share 1 electron for each fluorine. So in this case, these 2 electrons are being shared by both xenon and fluorine. Same with these 2, and these 2. So all of these can become single bonds. So now if we look, each of my fluorines, if we count them up, ends up having 8 valence electrons, a full valence shell. My xenon, however, will have 2, 4, 6, 8, 10, 12 electrons. And so when I'm looking at this and I'm counting up electron groups, these 2 here, these are lone pairs, and then I have 4 bonding groups. So I have a total of 6 electron groups, 4 of which are bonding, and 2 are lone pairs. So use my molecular geometries chart. I end up seeing that with 4 bonding groups and 2 lone pairs, my molecular geometry, or the shape of my molecule, is going to be square planar. So with 6 electron groups, our overall electron geometry is octahedral, but because we're not going to see these lone pairs in the shape of our molecule, our molecular shape is square planar. So if we had the molecule flat on the board, we would have our fluorines arranged out like this, almost in a square. And then we'd have 1 lone pair coming out of the board and 1 lone pair going behind the board in space like that. So I'm going to do one more for you guys, and then I'm going to have you guys practice one. One that I'm going to do is going to be sulfur hexafluoride. So again, I'm going to start off drawing my central atom, which is going to be my sulfur. So sulfur is our central atom. Sulfur is going to have 6 valence electrons. And then again, I'm going to space my fluorines evenly around my sulfur and add their valence electrons. And so this one is going to be a little bit more interesting. What I know is I have 6 fluorines here. Each of these fluorines just needs 1 more electron in order to have a full shell, because each of these fluorines have 7 valence electrons. So again, they want to get to 8. So what I'm going to do here is I notice that my central atom has 6 electrons and there are 6 fluorines. So I can divide each of my sulfur's electrons and share them with each fluorine here. And of course, each of my fluorines is going to share its lone electron or its electron that's not paired up with my sulfur in order to form a covalent bond. And so in each of these instances, these 2 electrons are being shared by sulfur and fluorine. These 2 are being shared by sulfur and fluorine. These 2, these 2, these 2, and these 2. So all of these pairs, these are all going to form a single bond between our central atom and each of these fluorines here. And so what we have here is a sulfur atom covalently bonded to 6 fluorine atoms. So if I count it up, I have 1, 2, 3, 4, 5, 6 total electron groups. all 6 of which are bonding groups. And so I have 0 lone pairs. So using my molecular geometries chart, I see with 6 electron groups, 6 of which being bonding and 0 lone pairs, my molecular shape is going to be octahedral. Alright, so I just finished doing some examples for you guys. What I want you guys to do now for practice, you need to do this on a piece of paper, take a picture of it, and then turn it into this assignment on Google Classroom. I'm going to have you draw the Lewis dot structure, tell me the number of electron groups, the number of these groups that are bonding groups, the number of these groups that are lone pairs, and determine the overall electron geometry as well as the molecular geometry for these 2 molecules. So PCl5 as well as CCl4. Okay, so here we have 1 atom of phosphorus and 5 bonded to 5 atoms of chlorine, and here we have 1 atom of carbon bonded to 4 atoms of chlorine. So again, make sure you include all this information for number 1 and for number 2, and then turn that in to Google Classroom once you're finished.